Hello again, calculus students. This is Mr. O saying hi from vacation. I'm actually probably on an airplane flying back from Europe at this point in the excursion. So, hello from 30,000 feet in the air. Here is your warm-up for the day. Why don't we pause here for about 5 minutes so that you guys can work this out. Okay, we're back from pause, so hopefully we had a chance to work this all out. What we are looking at here are two different integrals that we are going to find. Hopefully you recognize that these were going to be u substitutions. For number 1, our u is going to be 1 minus x squared. That makes the du equal to negative 2x dx. We have the 2x dx. We do not have a negative, so we are going to bump a negative to the outside. So what we're going to be looking at here are, so there's my u, so I'm going to have a negative, there's my du. I'm going to have negative. This is a square root in the denominator, and so that is my u to the negative 1/2 power, and then I have my du. And I had the negative out front to account for the fact that we had negative 2x as our du, and we actually have positive 2x dx in the original problem. So, we're going to do the antiderivative. That is going to mean that we're looking at our u is now going to be to the positive 1/2, because we are going to add 1 to our exponent. We are going to get the reciprocal of that, and that is a positive 2. We have the negative that we had out there originally, and of course we are going to have r plus c. So when we back substitute in our u value, this is going to turn into negative 2. Parentheses, actually, check that, not parentheses, the square root of 1 minus x squared, because we'll take care of that 1/2 power, and then of course we're going to have r plus c. For the second problem, we are also going to have a u substitution. And within that u substitution here, we are going to have our u value, this time, be inside the parentheses. That's going to be our x cubed. And that is going to make our du equal to 3x squared dx. And of course we have the x squared dx, but we don't have a 3, so that means that we are going to put a 3 in there. That means we also need a 1/3 outside. So what that's going to mean for us is we're going to have a 1/3 integral, and then we're going to have sine u du, and that's what we're going to have left. So, integral of sine, okay, so 1/3. The integral of sine, the antiderivative of sine u, is going to be negative cosine u, so negative cosine u, of course r plus c, and then all we need to do now is back substitute in our u value, so our final answer here would be negative 1/3 cosine of x cubed plus c. And that's going to take us into the notes section, which is going to be the second fundamental theorem of calculus. Okay, so the second fundamental theorem of calculus, as you can see here, is going to entail the fact that the derivative of the integral of f of t dt is going to equal f of x. Okay, so what we're looking at here is the derivative of the integral of f of t dt is equal to f of x. What we're really saying with this is that derivatives and integrals are inverses. Okay, so what we're looking at here, we're taking a derivative of an integral of f of t dt, and it's just going to equal f of x. So notice a couple things right here. Number one, we have a lower limit of integration. That's any number. Does not matter what number is down here. Any number can go right there. Up top here, the upper limit of integration right here is x. And so what that means is we are going to get f of x as a result, because what's going to happen is we're going to plug in the x right there. Plug in the x into the function, and that is going to be the result. So, okay, so that means my dog needs to go outside, so it should give us some peace to work with for a little bit here. So, for the first example, what we're looking at here, we are finding the derivative of the function that we're given here. Okay, so here's our function, big F of x. We have our integral from 0, okay, that works, that's any number, and then the upper limit of integration here is x, excellent, that's good, and then here is the function, okay, here's the function right here in terms of t. So what's going to happen right here is, as we saw up here, we are going to substitute x in for t. We're going to get f of x at the end. So here's the function right here. Okay, so we're going to plug in our x into that function. So the result is the cube root of, instead of t squared, it's now x squared. Instead of plus 5t, it's now plus 5x. And I'm sure you're sitting there like, okay, now what else, right? What else do we have to do? Well, nothing really. That's actually it. When the upper limit of integration is simply x, then all we need to do is just substitute x in for t. Okay, so example number 2 is also very straightforward, because once again we have a lower limit of integration that is just some number. In this case it's -3. Our upper limit of integration is x, just like it was last time, and we're taking the derivative just like we were last time. So we're taking the derivative of an integral, which means we're going to take this x, this upper limit of integration, and plug it in for all of the t's. So what we end up with is, instead of t, it is going to be x minus, instead of secant squared t, it's going to become secant squared x. And that is actually the result. And I know you're thinking to yourself, well, that's just way too easy. And for situations when we simply have take the derivative of an integral, and the lower limit of integration is simply a number, and the upper limit is simply x, then yes, it really is that easy. So what if we come to the scenario where the upper limit of integration is not simply x, like what you see right here? So I still have a lower limit that's simply a number, like 2, but this time the upper limit of integration is x cubed. So this time we're actually going to need to do a little bit more than we had to last time. Okay, so what we're looking at here is, again, we're going to be finding the derivative. Still the same instructions as last time, so we're still finding big F prime of x. Okay, those instructions from problem 1 and 2 are still in existence. And so what we're looking at here is we are going to do a simple substitution. Okay, so that means we're going to get 1 over, and then instead of t, now our plug-in number is going to be that x cubed right there. So it is x cubed squared, because it was t squared, so now it's x cubed squared. And then the extra step that's going to be happening here is a chain rule. So what we have happening here is we are going to end up multiplying by the chain of that upper limit of integration number right there. So x cubed will become 3x squared, the derivative of x cubed, and that is the extra step that's going to happen when our upper limit of integration is something other than just simply x. And we can go ahead and simplify this out just a little bit. This is going to become 1 over x to the 6th power times 3x squared, and then we can simplify that even more by looking at, well, let's see, x is 6 on the bottom, I've got an x squared on top. That is going to give me 3 on the top over x to the 4th power. And then finally, for our last example, same overall concept, but this one's a little bit different because, if you'll notice, our upper and lower limits of integration are, neither one of them is simply a number. So when we were looking at the second fundamental theorem of calculus, this worked for when we had an actual numerical value, but this is not the case here. We do not have either numerical value. Both the upper and lower limit of integration are x, and x plus 3 in this case here. So what's going to happen here is we're going to want to break this up into two separate integrals. So remember, we're finding the derivative, so there's a big d dx kind of around the entire thing. And then what we can do is we can look at this from x to some value a, and then we are also going to look at this integral from that same value a to the final upper limit of integration, x plus 3. Okay, so what we've done here is we have broken this up so that we have the integral from x to a and the integral from a to x plus 3. So together, that's going to make the whole integral from x to x plus 3. We're just using some value a as kind of the stopping point in between. So, a couple of things we can do with this. If you recall, from when we first started doing integration, when we were doing it using geometry, when we were making geometric shapes with them, one of the properties that we learned about was that if these are switched, because they're backwards from where we want them, normally we have the a value on the bottom and the x on the top. If we want to switch those around, it actually makes this whole thing the opposite. So I'm going to turn this into the opposite sign right here. So that's going to give me, okay, so we're still the derivative, d dx, okay, and this time I'm going to take this piece and write it first. It's addition, so it doesn't matter what order it goes in. So a x plus 3 up here, 2t minus 1 dt. And then this is going to become subtraction now because we're going to switch these around. So instead of plus, it's going to become minus. And then we're going to switch these around a to x. So what that's going to do for us is give us our 2t minus 1. And of course our dt. And then close our bracket. So what this is going to allow us to do is apply the fundamental theorem of calculus twice. What that's going to mean is we are going to substitute x plus 3 into our function right here. And so that's going to give us 2 times, and then instead of t, it's going to be x plus 3 minus 1. So there's my 2t minus 1 with x plus 3 as my t. And then I'm going to be subtracting the whole thing now, and this one's going to be 2t minus 1, except I'm going to be substituting in the x. So 2x minus 1 is going to be the second piece right there. And then it's just a matter of cleaning this up. And so this is going to give me distributing 2x plus 6 minus 1. And then if I distribute the negative here, I'm going to get minus 2x plus 1. Well, my minus 1 and my plus 1 are going to simplify out. My 2x and my minus 2x are going to simplify out. So in the long run, the thing I'm going to end up with at the end is simply the number 6. So what we had was we had to break this up so that we could apply the fundamental theorem of calculus twice, because I needed a number, a simple numerical value. In this case, I just chose a as in any number between x and x plus 3. Remember that we flipped it around. That's why this became negative over here. That's what happens when we flip the upper and lower limits of integration. And then it was just a matter of substituting my x plus 3 in and substituting my x in, and then subtracting the results, putting them all together. Okay, that should take us to our worksheet, which should look something like this. So we're going to work through these two examples together. If we take a look at example 1, which is right here, okay, right here, we're finding h of x is equal to the integral from 0 to x of f of t dt for f of x shown in the graph below. So here's the graph, and we're going to find h of 2. So if you recall from what we had done geometrically, what does this mean? This means from 0 to 2, right? Lower limit of integration is 0, upper limit is x, but that's now actually a 2 because we've got h of 2. So what that means is, what is the area between the graph and the x-axis from 0 to 2? So if we take a look at what that actually means, we're looking at all of that little area right there. So what we just need to calculate that particular area. So that's a rectangle 2 by 2, so this is simply a value of 4. When we look at part B, h of 3, remember we're talking about from 0 to x, so in other words from 0 to 3 now, because our x is now 3. So that is going to mean we're looking at the area from 0 all the way to 3, which would be all of this area right here. So that is going to be 1, 2, 3, 4, 5, 6 boxes, and then this is a half of a box, and so that actually comes out to a value of 6.5, or 6 5/10, or 6.5. And then if we're looking at part C, it says find h prime of 2. H prime of 2 is going to really mean f of 2. If you recall what we had talked about with the second fundamental theorem of calculus, the derivative of an integral is just going to mean plugging that x value in. The x value happens to be 2, so what we're really saying is what is f of 2, and the value of f of x when x is equal to 2 would be the y value of that point right there, which happens to also be the number 2. Similarly, for h prime of 3, now we're saying the value of f at 3, which would be, here's 3, so the y value of that point right there, which happens to be exactly 3. Okay, for example 2, again, we've got our integral from 0 to x, just like we did last time. If you'll notice, this is a very different kind of graph. You'll notice that we start off below the x-axis, so we're going to have some negative area to deal with here. And then we're above the x-axis, so we're going to have some positive area here. And then depending on how far we go, we might have some negative area down here again. So if we take a look at what we've got for g of 4, g of 4 means that we are talking about from 0 to 4, okay, from 0 to 4, f t dt. So we are going to find the area from 0 all the way to 4. That's going to include this region right here, and then this region all the way to 4 right there. So we've got some negative area right here, and we've got some positive area right here. So if we take a look at what's going on, let's see, well, if I look at this area right here and this area right here are identical, but one's negative and one's positive. So really, g of 4 is really just talking about this area right here, because everything from 0 to 3 is going to be 0, because I've got the exact same negative and positive areas, which just leaves me with this one little piece of positive area right there, and so what we end up with is g of 4 is simply equal to 1. The area is equal to 1. G of 2, for part B here, we're going to be talking about, okay, well, we've got this negative piece right here and this positive piece right here. Well, if you'll notice, this piece and this piece are opposites. Well, they're the same, except one's above and one's below the x-axis. So really what we'd be talking about here is just the area right here, which happens to equal -1. Alright, and then finally for part C, we are trying to find the x-coordinates, not the whole ordered pair, but just the x-coordinates of the minimum and maximum of g in the interval between 0 and 6. So since g is the antiderivative, or the integral of f, then that means that this graph that we see here, f of x, is the derivative of what we're talking about. So if we're talking about where the derivative is equal to 0, we'd be talking about right here and right here. And so if we want to talk about a minimum or a maximum, This point right here is when we're changing, when our derivative is changing from negative to positive. So that's going to make this location here our minimum point. What is the x value right here? It is 1.5. It's right in the middle of the 1 and the 2. Similarly, right here, our derivative is changing from positive to negative. That means that our maximum point is happening right here, and so that makes our max right in the middle of 4 and 5 at that point, making it 4.5. So our min is at x equals 1.5, and our max is going to be at x equals 4.5. So there you go. Good luck on the rest of the worksheet. There are problems out of the textbook for this area down here, and then on the back are more questions like these two examples that you see right here.